So welcome back, everyone. Today we're very pleased to have John Shelf, who's the department head for computer science at NERSC, and so he's responsible for many of the wonderful decisions made about what hardware you guys get to program on up there, be it Hopper or Edison, and all the planning gets involved in that. And so one of the interesting things about today's lecture is that it's going to describe a bunch of software tools that you may want to use in your class projects. You've been writing relatively low-level code, MPI, OpenMP, and so forth. But what a lot of computational scientists do is that they use frameworks, higher-level programming systems that try to hide a lot of the details and let you, express your scientific algorithms at a higher level. And there are a lot of different kinds of frameworks for different areas of science, and that's what John will be talking about.
So there are two things that cause us to move towards higher-level software engineering and abstractions for designing our systems. And the first is, of course, hardware complexity. The hardware is exceedingly complicated, and we need to have abstractions to hide the nature of the parallelism and the complexity of the machine. And then the second, I'm going to talk about how the complexity of the simulations themselves and the software itself is actually motivation for creating higher-level programming constructs. So this is kind of the schematic of our growing hardware complexity here. This is to root you in what is happening right now and why we're actually redesigning a lot of our software infrastructure to meet intercept these changes in the hardware architecture. So, the first thing is that power has become the leading design constraint, and so future performance growth is actually leveling off because of the power constraint. This is a DARPA 2008 report, which shows, this is the historical progression of improvement in performance in machines using historical approaches. And we're not going to see the kind of exponential growth rates that we've expected in the past. And now our mitigation for power being a limiting factor is to halt our exponential increase in clock rates and move towards parallelism for all future performance growth. What that means, though, is that for our leading edge systems, we are the only way to maintain our historical growth path is to double the number of cores every 18 months instead of doubling the clock frequency every 18 months. And that puts us on a course to having a billion-way parallel systems in the not-too-distant future, 2018. So parallelism is now growing at an exponential rate. The second thing is that memory density is no longer improving at historical rates. This is a problem, a cost problem for future systems, but it's also a problem for parallelism because if your memory technology is no longer improving, it causes the size of problem relative to the parallelism to be smaller compared to the amount of parallelism, which just pushes you towards strong scaling, which I believe you've already discussed in this class. And that was the reason used for many years to explain why we should never invest in parallel machines and should always stick with Cray vector systems. So you should be very afraid of Amdahl's law. And the last but not least is that communication costs, the cost of moving a bit of data around in a machine is currently everything we do preserves flops, but as we move forward, the cost of computation is reducing, but the cost of actually moving the data to that computation is now exceeding the cost of performing an operation upon that data. And this really deeply changes our programming model. So by 2018, cost of a flop will be less than the cost of moving the data to said flop. And then last but not least, we've come to expect the hardware to be reliable, but there's concerns for large-scale systems that it's going to be partly our problem too as software engineers. So those are the complexities, facing us in terms of the hardware architecture. But then, if you're actually doing big scientific simulation codes, or for that matter, if you're doing massive web interfaces and working for Google, you have a huge amount of application complexity. There are so many, just in the science area, there are so many parts to the application that no individual is expert enough to understand everything that's going on in the code. This is also, though, true. Frameworks are actually born out of the business area, and we're applying software engineering practices to make large multidisciplinary codes in the sciences tractable. So you'll see frameworks used in both places. I will speak from my perspective as a scientist who's worked with these multi-physics codes. So, you know, leading edge HPC system code, it's multidisciplinary, it's multi-institutional, multinational efforts. These things are like building the Large Hadron Collider, you know, that it requires a village, maybe even a city to get future experiments done. So, you know, advanced parallel languages are nice, and they are a necessary condition for us to make the programming of future systems tractable, but they aren't sufficient. You also need to have disciplined software engineering practices and higher level frameworks in order to hide the complexity and organize your code teams. So you need higher level organizing constructs for teams of programmers, and the languages and your software engineering discipline need to work together for a complete solution. So this is from my distant past. I used to work for the General Relativity Group at NCSA in the 90s. And so this is kind of like a brief history of the kinds of projects and how we had growth over the time that I was there. So, you know, when I first arrived, there was, they were doing this NASA Neutron Star Grand Challenge, and that was our first parallel code. We ported to like a CM5 or something, and that was a 5-institution effort to combine together people who are experts in neutron stars with people who understood Einstein's equations and how to simulate those going forward in time. The very next project, so this project was ending about the time I arrived. The next project involved 8 US institutions across 5 years, and that was to actually simulate the collision of black holes, which is an important event for gravitational wave observatories. The most recent project, and this is after I've left the group, this is what they're working on now. It's a 10-year project involving 10 institutions, 6 different countries. It involves people who are experts in general relativity, which is the GR, hydrodynamics, chemistry, because there's chemical reactions happening in the clouds that surround these stars, radiation transport, analytic topology. None of these people, a priori, completely understand what each other is doing, but they need to understand the interfaces of what they're doing so that they can put together this very detailed simulation of the collision of core collapse supernova, which involves all of those disciplines. So these are large, geographically distributed, multidisciplinary teams that span multiple countries. You can't just throw, you know, SVN or Git or whatever you're using these days, you know, is insufficient to tame, you know, to get these people to actually work together as a disciplined team. You know, this is another example that, you know, you're seeing some of these codes, they have like hundreds of authors on papers for some of these simulation codes that they're developing. So very, very complicated codes, look like traditional big science experiments. All right. So for this reason, a lot of us as a coping mechanism have developed frameworks. And the one that I worked on was called Cactus, but there's others. Chombo, which is Phil Colella's framework up the hill here for AMR. There's Sierra, which is at Sandia National Labs, and that's for finite element simulations. In theory, to prevent bridges from falling, but in practice, I believe, to design nuclear warheads. But it's, you know, finite element simulation code has to be very trustable because you'd like the bombs to go off when you want them to and not go off when you don't want them to. And then you have UPIC, which is a framework developed at UCLA for particle and cell codes, which is a very large class of simulation codes. And the purpose of the frameworks are to clearly separate the roles and responsibilities of your expert programmers from that of the domain experts. If you start letting them mix together, then you get all these wars about Fortran versus C++, or these days Python or Ruby on Rails, what have you. And you also end up having you know, really smart scientists completely mangle your elegant code, and you don't want that to happen. It also defines your social contract between your expert programmers and your domain scientists, which makes it clearly established rules of what code they are to touch and what code you, the expert computer scientist, are to touch. It enforces also a software engineering discipline so that when you make an agreement, when you create a framework and you document the APIs and the data structures in your framework, this also is a kind of a style guide that keeps the programmer who likes to, has a particular structure of arrays from stepping all over the guy who likes arrays of structures or what have you. The framework actually causes people who are working in the same layer of the code to actually work together in a collaborative fashion, and so it acts as your style guide. The last two things are really important, and I've added some features to the end of this presentation to talk about domain-specific parallel abstractions. The core of the design of a framework actually is to come up with the parallelization abstraction for your particular dwarf that you've selected. So, Cactus is a block-structured grid, PDE solver dwarf. But we also have an example in this presentation from Petsy, which has some great abstractions for matrix algebra, in addition to having some good stuff for and UPIC is for creates a abstraction for particle and cell codes. And that enables your scientists, or your users, the ones that aren't experts in the details of a parallel machine, to get performance by plugging in little serial plugins to the code. And they don't have to reason about parallelism, they don't have to reason about scheduling or correctness. You, the expert programmer, get to take that off of their hands. And so that's, allows the scientist to code nominally to these serial plugins that are invoked by the parallel driver. And the parallel driver is your way of abstracting the complexity of the method of parallelization, the dwarf that your code represents. So when it comes to these parallel drivers, and this is just the general design principle, the thing that was curious with frameworks is that in the past we've always thought of frameworks as being kind of ad hoc software engineering things, and nobody could stay awake in software engineering class in college. The curious thing is that when we got groups of these people together that had completely independently developed frameworks, we're shocked at, despite the fact that they were for completely different areas, disciplines, completely different sets of people, they all had these three common principles that were recurrent in every single framework that was what I consider successful frameworks. And the first is that you relinquish control of main. Usually when you write a program, the first thing you're doing is main, int, argv, argc, whatever. You don't see that anymore if it's a real, genuine framework. Main disappears as a concept. You're just creating plugins for a predefined architecture. The second is that these little plugins that and the reason relinquishing control of main is a good thing, actually, is it allows your framework to actually decide how to parallelize things, how to lay out your data structures across a parallel machine, and when to schedule things, when to invoke things to run. And so that's the really important feature of why you want to relinquish control of main. Second is that each of these modules, these plugins that you have, must be stateless. Yep.
So I guess one other reason is that you can run it on your laptop in sequential mode, and then take the same code and then import it to Hopper, and it runs there too.
Absolutely, and that's another one of the things that I probably won't get into in this, but we had this desire to develop on your laptop on the train into work, and take that very same code and run it in a supercomputing environment. And the Linux environment in your laptop can be very different from the environment in the supercomputer. Less so now than it used to be, actually, but frameworks can also enable that kind of ergonomics, yes, absolutely. Also, different machines will have different requirements for optimal layout of data structures and scheduling and such. So another thing is that a module must be stateless. And this is very important for managing memory consistency. You can make it so that the modules are not stateless. And we observed that frameworks that attempted to incorporate, let people include state in their modules tended to fail because managing memory consistency is very difficult. So stateless modules, and then the modules that you plug in only operate on the data that they're handed through the interface. And you'll also see that there's some programming models that operate like Silk is a programming model where you annotate a subroutine to say that it has no side effects and it only operates in what is handed. And that's very important because then that gives this main, the driver, a lot more freedom to schedule things if it knows that it'll only operate in the data that it was given.
So just to clarify for everybody, stateless means no global variables, no common blocks.
You got it. And the inverse of stateless, is that it only operates in the data that it has. It doesn't carry state between invocations, too. So, another way you can think of drivers is think of it as coarse-grained functional style of programming or coarse-grained data flow. I tend not to say that too often because people who actually did use data flow languages in the 80s have a very bad it has a bad rap, but and yet everything that I see reemerging as we confront massive parallelism has very much of a data flow functional flavor to it, and so they don't want to say those words, but it's happening. And so you want to be able to flexibly, your DAG, your data flow graph, is directly expressing the scheduling constraints so that your driver can schedule things efficiently. So, here are the other frameworks. They use the same principles, similar motivation, but completely different fields and completely different idiom for parallelism. So you have a dwarf. The dwarf talks about the structure of your problem. You got your sparse matrix, your particles, your dense matrix, so on and so forth. But your idiom for parallelization is how you actually take a dwarf and create an abstraction to describe how you'd actually implement a parallel program. And once you come up with a really good abstraction, then you can build your framework around that, the data structures and the scheduling. And so Neuron is for parallel neurodynamics simulation. You got Sierra's finite elements, TechX, PicCode, Chombo for AMR. And the common benefits and modularity, in addition to the things that we mentioned earlier, in that I probably should have added the running in your laptop and running in the supercomputer to this list, but you get modularity, so you get composition using higher level semantics. Whoops, I'm supposed to point using this thing. I just love to point with my hands, so okay. So modularity, composition with higher level semantics. You got your segmenting of your expertise, so separating your expert programmers from your domain users. Unit testing, this is actually huge. You always are taught to do unit testing. When you actually create a modular framework that has these plugins, it hugely simplifies and enables you to automate the process of unit testing. And that's actually a huge deal, is because if you have to do a separate, completely different unit test for each single thing that you plug into a framework, then you're kind of screwed. Now you can actually have a completely automatic unit testing, which is great benefit. You get performance analysis, where you can actually separate your different components along modular bounds. Correctness testing, so you can that goes together with unit testing. So I'll just skip past that. It's based on reasonable semantic boundary. There's always an issue with performance analysis and correctness testing tools, is that they didn't understand actually the semantics of your program, so it's hard to make sense of their output. The framework enables you to define those along semantic boundaries. And the last thing is it enables better reuse of solver components. So this is now the other part of it is organizing your team of scientists and computer scientists together. And so this is the collaborative development. So computer scientists and domain scientists, you make an agreement and you can actually collaborate together more productively. No more arguments about C++ and Fortran. You don't have to teach your physicist about unit testing because they don't really want to know, it turns out. And so this enables you to smuggle that important feature in without having to teach them. Enables multidisciplinary development, so you could actually have people working in completely different modules that have completely different physics, and they don't have to 100% understand each other, but you have a common plug-in framework where you can bring together these components written by experts whose expertise doesn't necessarily overlap. It also makes some advanced CS stuff trivial accessible to your app scientists, and it makes sharing of the physics modules among the computational scientists easier. The hardest part in designing a new framework actually is to agree upon your data structures and your interfaces. People always think of the coding as a tough part. Actually, making your agreement on how to standardize your data structures always turns out to be the most difficult thing of designing a framework. And for this reason, there are actually different levels of integration, and it all depends on how willing the teams are to allow invasive changes to their work. So this is from a DARPA meeting we had in like 2006 to talk about frameworks. You got most engineering codes today are over here in this minimal component interoperability zone where, and believe it or not, so there's this guy from Procter & Gamble who talks about this. You want to simulate like a diaper. At Procter & Gamble, you got to simulate the diaper. And so you have to have a fluid dynamics simulation, you have to have kinematics, and you have to have even audio. You don't want the apparently Pampers if they crinkle too much. It's very annoying, and you don't want that. And so they take the acoustics, no electromagnetics, fortunately. They got the structures, the fluids, and the acoustics are all completely independent packages that you get from different commercial vendors, and they do not interoperate. So you take a few time steps with your fluids code, you output data, you read it into the structures code, and you take a few time steps in that, and you go round and round. More recently, some of these guys have gotten together and they actually decided to abstract the writing of the file so it actually writes into memory instead of a file. And so they can interoperate by agreeing to a standard file format and writing that into memory. And so it's really, they've normalized their data structure. So now they can actually have 4 independent simulations exchanging data by thinking they're writing files out, but they're actually really writing data structures into memory. But ideally, and this is what we do with Cactus or Sierra and stuff, you'd like to actually get everybody to agree upon the data structures so that they're completely modular and reusable by all of the different code components, and that's a fully coupled, deep component interoperability. So how much invasiveness are you willing to put up with? Wanted to point out quickly, people are always asking, what's the difference between a library and a framework? Well, the library, you own main and you invoke the library, and you have to describe to the library. A lot of library interfaces often have a lot of extra terms in the API so that you can describe how you actually chose to lay out your data in memory. And that can tend to complexify APIs if you have to make the library flexible in understanding data layouts. So you present a data layout to the library and it works with it, or the library says you can't lay out your data that way, in which case you have work to do. A framework, it's the inverse. The framework invokes your code as a plugin. You do not own main. You've agreed and normalized all of your data structures, and again, the thing that is invoked only operates in the data that it was given. So it's the functional semantics of the framework give you more scheduling freedom. This is also Kaushik Sen, who's here at Berkeley, and this is in Parlab, made this observation that parallel program could be composed of parallel and serial sections, and a serial code can invoke a parallel library. You can think of the framework as doing kind of the inverse of that, where it's the framework is pre-running, and it invokes your plugin, which is kind of a serial component. And you can think of having different frameworks for different patterns, parallel patterns. So now, talking quickly about separation of concerns. You have your, this is your developer roles. These names here come from old Microsoft report. So Einstein is an expert, in what they do. Mort is an idiot, and so you just don't want them, messing with your stuff. And Elvis can dance. So that means they're conversant in that particular piece of code. And so a framework, I think in Parlab we talked about a performance layer and a productivity layer. In a lot of the frameworks that I've worked with, they actually choose 3 layers. And so you have the application layer where your domain expert, the guy who really understands the physics and general relativity, is Einstein when it comes to the GR. But he's Elvis, he's conversant in the different numerical libraries that could be used to solve, create a simulation of the problem, but they're not experts there. And they have all sorts of theories about how hardware works that are generally wrong. And so you learn to just nod and say yes. So the next is you got your solver experts, and these are the people who actually write the core numerical libraries for these codes, and these folks really need to have a pretty good understanding of the hardware. They aren't like computer architects, but you really have to understand how caches and all that stuff works to do a good job of writing a solver library. And you're reasonably conversant with your customers, who are the domain scientists. And then the last one, these are the people like Paul Hargrove that like to write the low-level code, the communication libraries, schedulers, all of the software infrastructure that that implements the parallelism underneath the covers for your solver team. And this was just I think there's probably too many words that used to make sense to people who worked on Cactus but don't make sense here. This is a concrete example with the solvers that we had for a particular Cactus code. These guys up here saying, I want to do a neutron star simulation. I need a general relativity plus adaptive mesh refinement and hydrodynamics. The solver guys talk about an elliptic solver, and you get a choice of multiple elliptic solvers here. And then down here, the driver layer people are talking about halo exchanges and just the low-level constructs to implement the parallelism. Last but not least, so they enforce coding conventions, encapsulate a domain-specific idiom for parallelism. The death of any framework is to try to become too general. Then you have to, a framework that is too general becomes damn near impossible to use, so they tend to be developed around a particular set of problems that have a consistent set of needs. And this is just reiterating some stuff that I said earlier. All right, so let's get into an example. So Cactus code was started in like 96 at NCSA, and then it moved with, our group moved to Germany, and so it moved with us to the Max Planck Institute in Berlin, and that's where it got finished. It was to solve thorny problems in numerical relativity. And it wasn't just because of the complexity of the machines we were dealing with and the fact that NSF couldn't decide if the SMPs were the future or clusters of Linux boxes, and so this was kind of our risk mitigation for that. It was also to deal with thorny physicists to try to get them to work together. It was a framework for HPC code development and visualization, managed the increasing complexity of the codes that we were dealing with. Back then, MPI was pretty new. That's now a 20-plus years old. These slides are about 10 years old. And when these slides were 10 years old, I said that it was used for 10-plus years. It's still actively developed. And it also helps with our collaborations, multinational collaborations. So the purpose of the code was the NASA and also the European Space Agency and the US, they're building these gravitational wave observatories. And there's multi-billion-dollar projects. The idea here is that one of the last untested parts of Einstein's theory of general relativity is that the fabric of space and time should actually be able to ripple, kind of like you got acoustic waves, but actually space and time might ripple from giant events such as the collision of two black holes. And so they build these ginormous, interferometers here. So this is like the one over at the Hanford, Washington site here, and it fires a laser beam down this really long tube, and it'll if a gravitational wave actually passes through this thing, it'll actually subtly change the length of those tubes. And if you can detect that, it moves it like the size of the radius of a hydrogen atom. If you can detect that faint signal and separate it from acoustics in the area, then you could actually start, it'll create gravitational wave observatories. And the way this works is that you get two black holes and they start spiraling in, and there's a really well understood set of equations of what kind of waves they should generate. But the impulse that would actually be detectable by this detector is when those two black holes merge. And that's extremely complicated, extremely nonlinear. And so they wanted to have computer simulations to enable them to know what signal, characteristic signal to look for that represented the merger of those black holes. So Cactus was developed originally for doing these complicated general relativity type simulations. Another thing that they simulate with Cactus is we're trying to find out what the source of gamma rays are, and they suspect it's a particular type of supernova. But in order to fully understand it, you have to combine together the supernova guys who don't generally do general relativity, some chemists, and people who have the general relativity codes. And so a framework like Cactus enables us to bring those people together. So we combine together codes from Mike Norman, which do radiation transport, with all of these people here who do general relativity. It's still used worldwide, active user community of a couple of hundred people. It's also expanded in computational fluid dynamics, chemistry, and bioinformatics. So the features are that it provides this idiom for parallelism for these kinds of codes, these PDEs and block structured grids. And nominally, our developers will provide their redesign their Hydra modules so that they're these serial plugins. And when you plug it into Cactus, then Cactus becomes responsible for how it lays out the data structure across your parallel machines and enabling scaling performance. And this takes it out of the hand of your physicists and allows one team of people to create scalable parallelism on behalf of all of your different solver teams. The second thing that it provides is a build system that works uniformly across the many different kinds of supercomputers and laptops that are available out there, including Windows, as long as it isn't Windows 8. I can't help you if it's Windows 8. Nobody can help you, not even Microsoft. So you have this, it allows us, it's not magic actually. We didn't create the make to end all makes. We actually learn over time every time a new software environment comes out, and we put it into this known architectures file. And so it's really more of a social engineering mechanism where all of the things that we learn about optimization, code builds, and the different systems, we actually have a standard way of describing that so that one person can figure out how to make Cactus run in that machine, and then everybody in the Cactus universe benefits. So write once, run everywhere, laptop, desktop, clusters, petaflop, HPC. You got your modular application composition system, so you can describe how these different physics modules connect together, and it just handles all of the building of those modules and plugging them together. It kind of self-organizes the code for you. And then the last thing is language neutrality. You could write your modules in C, C++, Fortran, Java, lately Ruby on Rails, and it hides it completely hides all of the automatic binding and all the differences of the languages. So no matter, when you write your module in whatever language you want, you have no idea, it doesn't matter what language the other modules in the system were written in. So it enables, gets rid of our old religious battles about languages. So Cactus is basically, we refer to the body of Cactus, the driver, as the flesh, and these things that we plug into the flesh were the thorns. Over time, more and more of this modular functionality moved into the thorns, so maybe they should call it rows, but somebody already stole that name for a compiler, so we couldn't change the name. So it's Cactus, but this Cactus part is very, very skinny, and the thorns are very, very big. So a thorn is a block of source code and a little text descriptor that tells you what the what language it was written in, what you need to bind to, the bindings for invoking it, the initialization, the thing to call when you're evolving your simulation, and the thing to call when you want to shut it down. So you describe your interface, scheduling constraints, and any parameters that might be needed. The parameters are also important. So you'll have a module for, say, chemistry, and you need to describe to that module when it's only one tiny part of a very large multiphysics code. You need to be able to explain what the input parameters are for it. And you'd like to not have one parameter file per module. So they standardize the way that you describe the parameters so that, that all of any module that's plugged into Cactus will can read from a single parameter file, and keeps us from going crazy. The second thing that you have from the thorns is this thing called the driver. And the driver is actually where you implement your idiom for parallelism. The driver is the thing that decides how to lay out data across the machine, so your domain decomposition strategy. It implements the communication layer, whether it's shared memory, PGAS, or MPI, and it implements really the communication abstractions for your code. So in Cactus, for example, if you decide that at the time, this was really important because we had machines that they didn't have MPI, so they had completely different ways of doing communication between nodes. But let's say on a modern machine, you can have a driver that'll run on your laptop that's completely serial. You can unplug it and plug in a driver that implements MPI parallelism for a very large-scale machine. But it just so happens that Hopper is our machine at NERSC is way more efficient if you use PGAS type paradigm. So you can actually unplug that driver and plug in a driver that implements a complete PGAS abstraction for the communication. Now, here's the important thing, is that I only had to unplug one module, this quote-unquote driver module. None of the rest of my modules for the solver had to have a single line of code changed. And that's the power of creating these layers of abstraction, is that I can go to completely different machines and only have to just change the name of the driver code, saying that I want to use a parallel driver, I want to use a serial driver, and nothing else in all the rest of your code has to change. Just a single module, and you don't even need to know how that module works. So last thing is the flesh, and that's the thing that glues everything together. All you have to do is provide a list of the names of the modules that you want combined, including the list of the thorns that are your implement your physics, and then which driver you want to use. And the flesh just does all the right things. It builds everything so that it runs, and it starts running the code. Quick comment on idiom for parallelism. Stencils, PDE solvers, and block structure grids. Our idiom for parallelism is the halo exchange. So the central idiom is boundary exchange. So this is like you have one grid and you parallelize by domain decomposing that grid. then each local solver component performs its operation on these domain decomposed grids, and it has no idea, the local solver component actually has no idea how many grids are in the system. All it knows is that it was invoked and it's supposed to apply its operator to that local patch. And that when it releases the code back to the driver is just going to do the right thing. It's going to exchange the boundaries using whatever communication mechanism makes sense. So the driver, our original driver was called PUG, which is Parallel Unigrid, implemented MPI communication. From the standpoint of the person writing the code, you have no idea that it's actually domain decomposing the grid into these little blocks. All of your code looks exactly the same, but it handles the domain decomposition, the layout of those grids across the parallel machine, and makes sure that all of those halos are exchanged at the right time that you should exchange them. It also so happens, though, that this idiom for parallelism we used for unigrid codes also works for adaptive mesh refinement codes, which are a heck of a lot more complicated, where you can actually have refined meshes that are hierarchically laid out on the system in order to apply computation where it's needed. So it's just kind of a neat feature that we're able to tackle AMR using this same framework. All right, so let's just walk through an example of what it looks like to write a PDE solver in Cactus. And so we'll just start with the process that a physicist would go through when they're writing a new code from scratch. So let's just do the heat equation. Everybody loves the heat equation. It's like your hello world for PDEs and block structured grids. Or actually in this case, it's the hyperbolic wave equation. Sorry, not the heat equation in this case. So the hyperbolic wave equation says that I drop a pebble into the water in the middle here somewhere. This used to be an animation, but whatever. I drop a pebble in the water. It disturbs the water, and then that wave kind of propagates away from where you drop that pebble in. It's such a ridiculously simple equation that it's not real. But anyways. So you describe it as the wave in time is equal to the the del of the displacement in x, y, and z. So that's your analytic formulation. Now, in order to make this work on a computer, you got to discretize the solution, because you've got like you don't solve in the continuum on a supercomputer. Oh, shit. Yeah. You don't solve in the continuum. You actually have to take solve in discrete points in space and in points in time. And so that's taking that same wave equation in 3D, and now we're expressing it as a partial differential equation, a discretized partial differential equation. And so this is a centered, finite difference, second order stencil. So what I'm doing here is I'm saying, the derivative in the time direction, for example, is the difference between these 2 points divided by the time step size. So instead of actually having the real diffeq, we have a discretized differential equation. So now I take this guy, I lay it out. I lay out my pebble that dropped in the water. I lay it out on a two-dimensional grid, and I tell it what the spacing is in space and time, maybe apply some boundary conditions. But yeah, we'll just keep it simple. This is a simple problem. It's got an analytic solution, so after I write my simulation code with the PDE and the block structured grid, I could go back and compare it to the analytic solution and see if I got it right or not, which is great. So now we take that finite difference equation, we actually convert it into code. But you'll of course have to do all this other crud, like set all of your little parameters, your local variables. You have to open up your input and output files, and then you have to define your little finite difference thing as a triply nested loop, so you can go through X and Y and Z for the little stencil that implements your PDE. And after you write that code and you run it serially, you can go use MATLAB or Ploticus and you can see your wave equation from dropping your pebble into the water. All right, so that's fine. That's your standalone serial program. So now we want to put this into Cactus. So we really want to focus on just the part of the code that applies that little stencil operator to each of the points. And now you have to change this loop so that it only sweeps over the patch of the grid that when we'll invoke this as a subroutine call, and it'll only apply this operator to the patch of the grid that it's told to, because that's the rules that I told you earlier. It has to be stateless and only applies its operation to the part of the grid that you asked it to, and you can throw away all the rest of this code. And now suddenly you're inside of a parallel framework that's capable of scaling to the largest machines on the planet. And when you tell it to run this problem, it'll run in parallel, and it'll do the right thing in terms of laying out that data across a large parallel machine. And there's very little extra work that needs to be done on the behalf of the programmer. And so this is why you focus on just the physics. So there's less writing to do, and you get your parallelism, and I can also then plug this guy in next to something that implements other kinds of physics that on the same grid to create multi-physics simulations. Other physics being things like chemistry or radiation transport or other things like that. So this is kind of the architecture of your Thorn. So you got your source code. That's that little box that I excised out of the original code. So this little green box here, your source code just goes into this box and you invoke it as a subroutine call. Now you need to have this interface.ccl, which is just a simple text file that says, this is a C++ code and this is the entry point. Call this subroutine in order to invoke that piece of code. You have to give it a name so that the compiler knows which of the many subroutines that might be in that source file needs to be invoked when it's time for that to be scheduled. The other is a param.ccl, and that's where you describe your list of parameters for the module. So, for your wave equation in 3D, you'll get the grid, the 3D grid that it has to operate on. But say if you had other parameters like how big the pebble was that you dropped into the lake, you would create a parameter that says pebble size, and that would be an additional thing that gets passed into your subroutine when it gets invoked. And then last thing is schedule.ccl, and that's that DAG description of your DAG schedule. It says what the input dependencies and the output dependencies are for your code. Now, it's not a strict DAG schedule in that you actually have to connect everything together. It's more loose. It says you need to invoke this after the elliptic solver, before the chemistry, things like that. So it infers a lot of data flow stuff just from more general descriptions of when you need to schedule the stuff. And then the last thing is documentation and make information. And the make information is really just a list of source files, and it'll generate the make files for you. So now, that's the structure of the Thorn, and that's really the only part that our programmers really need to know anything about. And now there was this, there's of course the immediately realizable benefit of enabling people to collaborate together and taking care of your binding for different languages and all that stuff. But then there are these emergent things that happened because now the computer scientists could go hog wild and create all sorts of other modules that the physicists would never have anything to do with. Before we had Cactus, before we had this modular framework, if we wanted to do something really cool with the code, or the computer scientists wanted to do something really cool, they'd give us a copy of the code. We'd whine and say it was too complicated, so they'd give us a simpler copy of the code. We'd do our little thing like checkpoint restart or whatnot, and they'd say, ooh, that's really cool. And then they'd never touch that piece of code again because they were always concerned that we had somehow corrupted the physics in a way that they couldn't determine. Once you get a modular code like this, you could actually unit test everything, and it enabled us to actually create modules that were distinct and separate from what the physicists were doing, and we wouldn't get in their way. So the framework abstractions enabled our performance tuning. Oh yeah, and I was talking about something completely different without reading my own slide here. Okay, so let's take a let me take a step back here. First thing is that a lot of people say when you do these layered abstractions that it actually is a source of, it reduces performance. I argue that all the evidence that we have is well-designed abstractions actually enable performance, and they do not reduce it. And that, so you cannot, I think it's provably false that layered abstractions actually inhibit performance. They are actually your way of taking performance tuning information and encoding it in a way that can be used consistently by many different people. So you can get your 1% programmers to offer something to the 99% that don't understand tuning very well. But then the other thing that you can do, though, is use these abstractions to hijack the code in really novel and interesting ways. And one example was we had a Gordon Bell thing guide, like, what, 99 maybe? 2000? I can't remember when this was. It was auto-tuning. So the idea here is that because the driver is abstracted away in such a way that the user can't, the people who wrote the solver modules don't actually see when it's scheduling things and when it's exchanging boundaries. We replaced the original Pug driver with a driver that automatically tuned the number of ghost cells that were used in the PDE solver simulation. So this is what they call S-step communication avoiding these days. And so we actually put an S-step communication avoiding driver in that would actually execute, and then it would gather performance timing information, and then it would decide to add some additional ghost cells. And so then it could go 2 steps before it had to communicate. And when it communicates with a larger message. Now, the solvers that were plugged in, none of them had to change, and none of them had any idea that it was doing this stuff underneath the covers for it. So so it starts adding ghost cells, and it says, oh, that made it faster, so now I'll add more ghost cells. And after it runs a few iterations, it said, oh, that made it faster too. So eventually it adds 4 ghost cells, and so it can go 4 steps before it actually has to exchange boundaries, and then it tries different forms of compression, and it keeps on adapting and trying different things to improve performance, including changing, in later versions, changing the data layouts. So that was kind of cool. So having these frameworks enables you to smuggle in cool stuff like auto-tuning and communication avoiding mechanisms without, again, reuse all of your solver infrastructure. Not a piece of it has to change. Another thing that we did for like SC2002, every year we used to use supercomputing as a way to demo new things, new tricks. It also caused our code teams to actually finish things on time if you had a deadline like SC. So this is an example of a task farming simulation where you want to study a huge parameter space. So we had a web interface. It would have a master simulation at a supercomputer would be running the main task, and then something like a gravitational wave would be formed due to a core collapse supernova, let's say. But you want to understand how sensitive your result was to the input conditions. So you'd like to do kind of a parameter study around that event of the gravitation wave. So it would actually go backwards in time a little bit and would spawn off a bunch of smaller simulations with different choices of parameters so that you could see whether or not that event would never have happened if just the input parameters were just slightly different, or if that event was so inevitable that it would have happened no matter how much you tweak the parameters. And so they refer to this these days as uncertainty quantification. This is kind of like poor man's UQ. Is that it would actually spawn off sub-simulations, it would gather the data together and then say how sensitive that event was to the input conditions, which was really useful for some of our stuff. We also used it for Smith-Waterman DNA sequence generation too. Another thing that we're able to do with the driver is fault tolerance. Traditional fault tolerance mechanisms do checkpoint restart, where you take the entire state of the entire code and you dump it to disk periodically. And if your simulation fails, then you read the whole damn thing in from disk from the last known legal checkpoint, and you start over again from that point in time. And the fact of the matter is that this is just not feasible given the speed of I/O systems today. We can't checkpoint stuff like that anymore. So, what we're able to do with the driver is actually do localized checkpointing, where an individual processor could fail and it's able to recover its state and continue stepping forward without causing the rest of the code to restart. And so this is called localized checkpointing. And again, this is something that completely no change in any of the rest of the code. All we had to do was be very clever with our driver stuff. The localized checkpointing also enabled us, though, to do nomadic applications. So this is when the grid was really popular, and this was kind of fun. If the code can monitor its own performance and also understands all of the state inside of the code. So this is, by the way, a really difficult thing to do in a regular code. Sorry, I should back up a little bit. Because the Cactus code knows all of the parameters in your code, because you had to declare them in a parameter file, and it also knows every single array in your code because it's responsible for parallelizing all of the data structures in the code. That means it knows every important piece of state information necessary to move your code to a different location if you chose to migrate the code or checkpoint the code. That level of self-awareness is extremely valuable, because actually writing the code to save the state of your simulation is very tedious and difficult to write. So we hijacked this to enable a code to be running on a supercomputer at University of California, and that computer, though, was a shared resource. I think this might have been the Millennium Cluster. And so a load is applied, and it starts failing. It starts really slowing down because it's competing against some other job in the machine. So then it says, all right, I'm throwing in the towel. So it actually saves its state, and it looks around for another machine in the network. And when it finds another machine, then it moves itself over there. It FTPs itself to the new machine, moves itself over there, unpacks itself, and starts running again. So we called this the Cactus worm. And that was before the other worm, but it was a fun experiment. And this is some stuff more recent from our University of Illinois folks on hybrid models, other abstractions for parallelization, which I'll just kind of skip through. Another thing we had that was kind of fun is that we realized that you wanted to remote monitor your code. So this started as we added a module to the code, or Gab Allen added a module that would send text messages to your cell phone to tell you how your code was doing. So it would send a message saying, hey, I started running in the machine, and then it would say, hey, something looks kind of bogus here, so I'm going to crash now. And so it could send messages. Later on, apparently Cactus now has a Twitter account. So you can actually converse with the code. You can say, what is your current step rate, and it'll answer back. We created a web page, so we built a module that plugs into the Cactus. Again, it takes advantage of all the introspection of all of your variables in Cactus, and you actually can connect with your web browser to the Cactus code running on a supercomputer. And it's actually, the code itself, the simulation code itself actually becomes a web server. And you can query the code to see how it's doing and even steer parameters. If you go to the cactuscode.org website, you can actually log into a running simulation, and that they always keep running. So in our original version, this was the kind of cell phone that was what a smartphone looked like in 2001 when we were doing it. I've recently updated it with an Apple phone that's still obsolete. But anyways, it's kind of a fun thing, and we also have all sorts of remote visualization tools. So you can, again, that introspection enables you to connect to a code while it's running and do all sorts of fancy 3D viz, and that was kind of cool. All right, so that is it for the Cactus part of the story. I've got two other brief stories, to show that what another framework looks like. So PETSI is a very capable framework that does PDs and block structure grids, but I'm focused in this presentation on their interface for matrix algebra, which I think is extremely elegant. But you'll see that the same ideas and structures come through with a completely different framework than the Cactus framework. But I actually want to pause here and see if folks here have any questions about Cactus or frameworks in general. Yeah.
Earlier you showed all the benefits of Cactus, portability, parallelism, etc.
Mm-hmm.
And you said they were for free. Well, we know nothing's for free.
Yeah.
What's the cost of all this?
So first off, you have to be willing to adopt the data structures that Cactus defines. So you can't create your arbitrarily complicated structs and things like that. You actually have to learn what the data structure, there's a standard data structure for representing 3D arrays. There's a standard data structure for representing particles. And those are created by Cactus, and Cactus completely and 100% understands those. So you have to adopt the data structures that Cactus uses, and that pisses off a lot of people. So the hardest thing of creating Cactus actually was to get a room full of physicists to agree to use the same data structures and not actually writing the code after we made that agreement.
And so if you had a simulation which was multi-physics and had some physics that wasn't represented by Cactus, well then if you'd have an interrupt, then there'd be an issue.
There would be an issue, though. We over time, we're able to get particles and different things normalized and into the standard Cactus framework, taxonomy. If you choose not to agree, then there are examples of that. There's the fusion scientists. There were two different efforts. There was one led by TechX, and there was another one led by Princeton Plasma Physics. The TechX one was more like Cactus, where they said, we'll agree on our data structures and everybody will design modules that plug into our overall framework. People who didn't like that referred to it as the code that ate Manhattan. And then the other group said, we already have really well-functioning codes. Why would we want to go in there and change all the data structures? It's just kind of tedious. So the other group chose to hijack the file writing interface, because that's the only part of the code where so eventually you have to agree on data structures. So in order to share data files, all of the guys had to agree the file format when they wrote data out into a file. So that goes to those two different levels of integration. Their multi-physics framework actually exchanged files in order to enable these different packages to run, but it exchanged the files through memory instead of actually writing them to the disk. That's pick your strategy, and it's fine. Though the guys who chose the latter, the one that writes files to exchange information, did not benefit from being able to share the infrastructure for parallelizing. So each of them still continued to have to be individually responsible for scaling their code in each new machine that came along. Okay. Anything else? All right. Well, so I'll give you just kind of like a smattering of PETSI. So when I went from the NSF side of the house to the DOE side of the house, I learned that they have a different set of codes that are very popular. And so PETSI is a very broadly used library that originated from Argonne National Lab. And my thanks to Barry, Jed, and Matt and Carl. These are actually their training slides, though I added some annotations to them. So this is kind of the PETSI, the structure of PETSI. It is a bit of an eye chart, so I decided to annotate it. So, you have your outer layer here is that broader, how do you specify the mathematics of the problem that you're trying to solve? And now they have, very much like Cactus and very much like the question you were asking earlier, in order to get inside of their framework, you need to adopt their data objects. Now, they do have a library API flavor of PETSI, which allows you to describe more to PETSI what your data objects are. But for the really turnkey, framework aspects of PETSI, it's a much lower hanging fruit to adopt their data objects. And then the next question that when you're designing these things is, after I decide what the relevant mathematics are for my problem, I need to ask the question, well, how do I solve that problem? And that's where you have, after you normalize after you've agreed upon your data structures with their object-oriented, representations of matrices, vectors, and indices, it has this hierarchical stack of solvers that actually can be applied to solve the problem. And I mentioned that PETSI also does block structured grids. So in addition to the object-oriented matrix algebra stuff, it's got object-oriented grid management stuff, but I'm going to focus on their matrix thing since it's different than what the Cactus did. And then the last thing is, how do I handle the parallel computations? And so it has like these lower layer interfaces for managing the parallelization, the data layout on the computer system. So where was I going with this? Oh yeah, it's got visualization and debugging interfaces, much like the ones that I showed you for Cactus. So this is kind of like the high-level eye chart view of the data structures and the algorithms that those data structures that are layered on top that those data structures enable. So you have like the various kind of matrix representations, solvers. Yeah, so okay, so the stack in the bottom here is your fundamental, the very basic data structures, and then using these very simple primitives, you layer on top of that and you build up your matrices, and then you can build up different methods in a layered fashion here. So let's just go into vectors. So, for matrix algebra, of course, you got your vectors and your matrices are some of the fundamental data structures that you need for this to work. So this is kind of the way that you would go about creating a PETSI vector. So you say, vec create. It's kind of like a C++ constructor, but it has to work in Fortran and C in addition to C++. But then you can actually set things like whether or not it's a vector that you want to lay out in parallel across the entire machine, or if that vector is local, like the vector seek, or if that vector is a vector that you need replicated and kept consistent across the machine, so vec shared. So what they've done in the allocator here is added some additional annotations or features to enable you to describe that vector in a way that hints at what kind of layout you want on the machine for managing parallelism. And then, of course, you want to set your vector size, the local size, and so you have these little n's and big N's. The little n is the local size. The big N is the global size of the array across your parallel machine. And then you got your handle for the local piece of your vector that you're able to access. And then, of course, your destructor. And so this is kind of walking you through an example of how you can actually choose to lay out your vector in parallel or as a local only vector in the machine. This is kind of an example of using, so I said, you don't own main. In this case, you do, except that every operation that you lay out in here is implicitly data parallel, or really SPIMD. So the parallelism of the machine is not in your face. In fact, you don't have to see MPI com create and all of those things, all of the things that you do. If you just look at this code in its face, you don't know whether or not this is running in a parallel machine, a serial machine, a shared memory machine, or an MPI machine. the interface is abstracted away, the specific manner in which the parallelism in the data layout was implemented, which is kind of cool. So yeah, so this, if you want, you can actually be more specific, like create an MPI specific vector, or you can stick with the generic code and it'll do the best thing. The next thing is, after you create those data structures, you get to the operators that you apply to those data structures are also abstracted. So you know, you have your vec copies, vec scale, your vec max, your absolute values, norms, multiplies. Now, you need to know, in order to apply these operations correctly, how the data is laid out in the machine and whether or not it's a local data structure or a global one. The cool thing is that because that information is hidden inside of your type descriptor, when you invoke one of these subroutine calls, it does the right thing. If it's a local vector, it's inside of the data structure, the information to know that it's local, and it applies the local version of that operation. If it's a parallel distributed vector, all the information it needs to know about how it is laid out in the machine is hidden inside of the data type for that vector. I'm just going to move ahead. Similar things for the matrix creation and destruction, describing the dimensions of your local submatrix and where it embeds in the overall matrix that you've described when you create your matrix. This is kind of an example of how you describe the global shape of the matrix, and PETSI can actually partition that matrix for you across the machine. And of course, it has all the information about the shape of the matrix and how it's laid out in the machine, whether it's parallel or not parallel, again, is encoded inside of the data structure. So let's, and then you can also have, just like Cactus, this also because the PETSI completely and 100% understands the data structures, it makes it very easy to call a subroutine call saying, draw me a picture of this matrix. And so because it has that introspective ability with its data structures, it makes other ancillary operations a lot easier to create. This is a solver interface. I'm going to skip ahead on this, and I'm just going to talk. Then this is our final chapter here, and this is going to be talk about recent opportunities for data abstractions using frameworks. So as I mentioned, the machines are getting exceedingly complicated. Abstractions are extremely valuable for enable sharing amongst large code teams, but they are also extremely valuable for hiding and abstracting the complexity of your machine, and in particular, the way that you lay out the data on this machine. Today, it's especially important because, as I mentioned, the cost of moving the data is now exceeding the cost of applying an operation to the data. And as a result, data layout has become a top-tier issue for designing algorithms for future machines. So, all these little design decisions here are design decisions that an expert programmer needs to make in order to figure out how to optimally lay things out on a system. But when you're creating a framework or some kind of abstraction for all those design choices, you really want to think more in terms of this is the design flow for thinking about your abstractions. There's a lot of aspects of the machine that are important for performance, but not really that important. They're only worth 2 or 3%. So, maybe there's a lot of things about the machine that you can ignore because it doesn't really have a huge performance or power consequence. It used to be that we ignored data locality. We said that every processor in the machine we pretended were equidistant. And let me move ahead here because I realize I might be running out of time. 2 o'clock, okay. 7 minutes. 7 minutes, all right. Yeah, I'll get to the meat of this pretty quickly. So, so there are some things that you can ignore, and you need to be very judicious about what you make people worry about and what you don't. The other are things that you can actually abstract or virtualize. If you can come up with an automated method of parallelizing a particular piece of code, then you should do it. It gets it out of the face. There's other things that you want to unvirtualize. So for example, modern programming languages don't allow you to specify information about the topology of the problem that you're solving. And it so happens when you're writing the algorithm, you know in your head what the topology is, but the programming language doesn't let you express it. So you need to think of what things, if you had that additional information, what things would you want to ask the programmer to provide to you so you could do a better job of hiding, abstracting the optimization process away from them. So data locality creates some of the biggest questions moving forward for framework technologies. And this is the original chart here. You've got your double precision flop is still improving. It's costs you 100 picojoules today to perform a double precision flop, but in the future it's going to be about 10 picojoules. Unfortunately, the resistance of copper wire is not improving in each generation of machine, and as a result, the cost of moving the data, though, to that flop is not improving, and we're getting very to the crossover point where the moving the data is becoming the dominant factor. You know, right now we see NUMA issues, non-uniform memory access issues, but it's going to become an issue even for getting between processors in the chip. So, you know, we like to separate this into vertical data locality management and horizontal. The vertical is basically your memory hierarchy in the traditional sense, moving stuff from your main memory into little caches in the middle up to the CPU and back out again. And so we have various cache blocking strategies to deal with that. The thing that's really going to become a pain is if you imagine we're well on our way to having 1,000 of these processing cores in a chip within the next decade. And so if you have 1,000 of these cores in the chip and you build out chips, at least with processor cores because they're hot and two-dimensional, it's a two-dimensional planar layout, then eventually it's going to get to the point that cores that are nearby each other spatially can have a lot of bandwidth and low latency to communicate with each other, and cores that are at the opposite ends of this chip are going to have a really difficult time communicating with one another, to the point that even maybe cache coherence, we won't be able to extend it across the entire chip, so you'll have these islands or communication domains. This is a different manner of complexity than we've had to deal with in the past, and all of our programming environments today specify parallelism in the iteration space. That is, that you divide the work up evenly, but you provide no description of the topology of the chip or the topology of your problem. I'm going to skip this slide and just say that, so our old model, for example, with OpenMP is, I describe how to parallelize loop iterations by having a parallel do that says, divide all these iterations up equally amongst the processors in this chip, and the magic of cache coherence will pull all the data to the correct location. Now, that is extremely inefficient and completely ignores the topology of the chip and the topology of the process in the chip. So the new model that started to emerge is this, what we call a data-centric model, which now you describe when you allocate your data structure, much as I was describing how PETSI describes the allocation of its data structure, except this is going to happen in your cell phone, individual chips, not just HPC. It's going to be all programs. You want to describe and embed into the data structure how it is laid out in memory, and then your loop statements, the actual computation, should operate on the data where it's located. And that's a fundamental inversion of the current way that we program these chips. You know, and so this is kind of, oops, that is in the way. This was one kind of cartoon for how this could work, where you actually describe the layout of your data structure with building it up in a hierarchical statement, and then when you allocate that data structure, that is the layout on the chip. Let me delete something here. Animation has failed me here. All right, I deleted that. All right, come on. All right, and then every place else in your code, all your do loops, they execute the iteration where the data is resident. And that enables you to have one place in your code where you allocate the array to describe how things were laid out. And not a single line of code where your loops are needs to change from then on. This has the added benefit of you don't have to write all sorts of loop blocking statements where this triply nested loop would quickly become a quadruply nested or six nested loop in order to block things for cache locality. So this concept is actually starting to get formalized into frameworks in the future where they've raised the data layout and the data locality as a first-class citizen in allocating the arrays. And so one example is TIDA, which is a product of the group that I'm working with, which centralizes and parameterizes all of that tiling information and makes it so that the runtime has all the information it needs to actually lay out this computation so that that near processes communicate with nearby cores and data that's far away is properly laid out, I guess.
So,
Yeah.
since time is short,
Yeah.
I was wondering, did you have a place to go or a summary slide for
Yeah.
all the different frameworks that are
Yep.
available at NERSC that people could use possibly for projects?
Sure. I'll make one final comment and then we'll talk about that. And so final comment is that you can prototype everything that you want in a framework like TIDA. And frameworks offer minimal invasion of the base language, but allows you to prototype and see if these are the right abstractions. If they are the right abstractions, the next step is to move them into directives, kind of like OpenMP has formulated a lot of our threading constructs that were in common use using frameworks in the base language, but then they put it into ignorable statements embedded in comments. Then the last thing is to migrate broadly usable ideas into a language extension. And very few things actually make it all the way to the end of this process, which is exactly why you want to have frameworks as your primary way of encoding abstractions. But if it is a very useful abstraction, you may very well see it in language. And people forget that most of what's in C++ was actually the way we were taught to program in C. And it was so, those things like inheritance and things like that were so broadly and commonly used, they simply raised it up a level and made it part of the language. So C++ and object-oriented programming, those constructs predate C. And this was an example where these statements here are part of the framework. And if you had it as a language construct, it would get rid of these additional statements, and that would be very valuable. Okay, so heterogeneity and homogeneity and summary. Oh, okay, so my slide that had a list of frameworks you could use is not here, but let me just list a few. So Cactus, of course, near and dear to my heart. So Cactus is a framework for PDEs. PETC is definitely well worth looking. It's had a very consistent set of constructs for data layouts. If you decide to do your own framework, then it's worth examining some of these other frameworks to see how they did it, and if you want to do it a different way, you can experiment with building your own framework. UPIC is a framework at UCLA for doing particle methods, and it's used by a lot of our accelerator modeling codes. Trilinos, oh yes, Trilinos is an excellent framework. Definitely worth looking at some things that are to the side of Trilinos. So look at, there's Cocos and Raja. Cocos and Raja are frameworks, but it's a new breed where they implement the parallelization strategy. They hide it inside of template metaprogramming for C++. And so a lot of the data layout stuff is in C++ template metaprogramming, but Trilinos is definitely good.
So perhaps we'll have a slide and post it later.
Yeah, I'll give you a list of good stuff, yeah.
Okay, so thank you very much.
Okay, thanks.